Consider for a moment the act of breathing. The invisible substance drawn into the lungs is often perceived as a passive background element of life, a transparent medium whose presence is acknowledged only when it becomes scarce. Yet air is neither passive nor trivial. It is an ancient, dynamic system that predates human civilization, shapes planetary behavior, and sustains every known biological process on Earth. The atmosphere is not merely a mixture of gases. It is a historical archive, a climatic regulator, and a continuous physical bridge between the microscopic interior of the human body and the vast mechanics of the planet. Each inhalation connects the lungs to processes unfolding thousands of kilometers away, while each exhalation contributes, however subtly, to the evolving chemistry of the global system. Despite this omnipresence, air remains largely unexamined in everyday consciousness. We breathe continuously without reflecting on where this air has traveled, how it moves, or how deeply intertwined it is with the rise and survival of civilizations. This documentary seeks to uncover that hidden continuity by tracing the journey of air from the moment it enters the human body to its circulation through the layered architecture of the atmosphere and its role in shaping Earth's past, present, and future. From the earliest stages of human awareness, attention has been directed toward visible structures: land, water, fire, and later, built environments. Yet the most expansive and dynamic structure on Earth has always been the atmosphere. Unlike oceans or continents, it has no solid boundaries, no edges that can be clearly defined, and no fixed form. Nevertheless, it is the most persistent and influential medium through which life unfolds. The atmosphere constitutes a vast, invisible ocean that envelops the planet, flowing continuously over mountains, deserts, forests, and cities. It moves across continents and oceans with little regard for political borders, transporting heat, moisture, chemical compounds, and particulate matter across immense distances. Human beings exist not beneath this ocean, but within it, immersed at all times in a fluid system whose motion never ceases. Breathing, often considered a mundane biological function, is in fact an intersection between the body and this global continuum. Each inhalation draws a small sample from the planetary atmosphere, while each exhalation returns a modified version back into circulation. The air entering the lungs is not newly created. It is a recombination of gases that have circulated through volcanic eruptions, polar ice, ancient forests, and countless organisms over geological time. This constant exchange highlights a fundamental reality: the human body does not exist independently of the atmosphere. Instead, it operates as a temporary node within a much larger, continuously circulating system. The boundary between the individual and the environment is therefore porous, dynamic, and constantly renegotiated with every breath. The path of air through the human body represents one of the most precisely regulated processes in biology. When air enters the nasal cavity, it is immediately subjected to conditioning mechanisms that adjust its temperature, humidity, and cleanliness. Nasal hairs and mucosal surfaces trap particles, while blood vessels warm incoming air to protect delicate internal tissues. From the nasal cavity, air passes through the pharynx and into the trachea, a rigid yet flexible conduit designed to maintain open airflow under varying conditions. The trachea divides into bronchi, which branch repeatedly into smaller bronchioles, forming a complex tree-like network within the lungs. This branching architecture maximizes surface area and ensures the even distribution of air. At the terminal ends of this system lie the alveoli, microscopic sacs whose thin walls facilitate gas exchange. The total surface area of the alveoli, if spread flat, would approximate that of a tennis court. Across these membranes, oxygen diffuses into the bloodstream, binding to hemoglobin molecules within red blood cells, while carbon dioxide diffuses outward to be expelled. This exchange is governed not by conscious control, but by finely tuned chemical gradients and neural regulation. Over an average human lifespan, this process occurs approximately 700 million times, sustaining cellular metabolism without conscious awareness. Respiration is therefore not merely a reflex, but a highly integrated physiological infrastructure that supports every organ system. The respiratory cycle establishes the fundamental rhythm of life. Adults typically breathe between 12 and 20 times per minute, resulting in approximately 20,000 breaths per day and hundreds of millions over a lifetime. This rhythm is maintained by respiratory centers located in the brainstem, among the most evolutionarily ancient regions of the nervous system. Unlike voluntary movements, breathing operates autonomously, adjusting continuously to meet metabolic demands. During physical exertion, emotional stress, or environmental change, respiratory rate and depth increase automatically to maintain oxygen supply and carbon dioxide removal. This regulation reflects the deep integration of respiration with cardiovascular and neurological systems. Importantly, respiration serves a dual purpose. It delivers oxygen, essential for cellular energy production, while simultaneously removing carbon dioxide, a metabolic waste product that becomes toxic when accumulated. This bidirectional exchange maintains the acid-base balance of the blood and stabilizes internal conditions necessary for survival. Breathing thus represents a continuous negotiation between the organism and its environment. Each breath aligns internal biochemical processes with external atmospheric conditions, reinforcing the idea that life functions not in isolation, but in constant dialogue with the planet. When air leaves the lungs, it does not disappear. It enters the broader atmospheric system. The atmosphere is a stratified envelope extending approximately 480 kilometers above Earth's surface. Although often described as a single entity, it consists of distinct layers, each governed by unique physical processes. The troposphere, the lowest layer, contains most of the atmospheric mass and is the site of weather phenomena. Temperature gradients within this layer drive convection, cloud formation, and precipitation. Exhaled gases initially disperse here, mixing with air masses influenced by solar heating and surface interactions. Above the troposphere lies the stratosphere, characterized by a stable temperature gradient and the presence of the ozone layer. Ozone absorbs ultraviolet radiation, protecting surface life from genetic damage. Without this layer, complex life would likely be impossible. Beyond the stratosphere, the mesosphere and thermosphere exhibit extreme conditions, with thinning air and dramatic temperature variations. At the upper boundary, the exosphere gradually merges with outer space, allowing atmospheric particles to escape into the vacuum. This vertical structure illustrates a critical point. The influence of a single breath extends far beyond the human body, contributing incrementally to a system that spans from cellular respiration to cosmic boundaries. The atmosphere functions as a thermodynamic engine, driven primarily by solar energy. Uneven heating of Earth's surface creates temperature and pressure gradients that initiate air movement. Warm air expands and rises, while cooler air contracts and sinks, establishing circulation patterns. Earth's rotation introduces additional complexity through the Coriolis effect, which causes moving air masses to deflect relative to the planet's surface. This deflection produces rotating wind systems rather than linear flows, shaping global circulation. These dynamics generate large-scale phenomena such as monsoons, trade winds, and mid-latitude cyclones. They also influence ocean currents, linking atmospheric motion to marine systems in a coupled planetary network. What is commonly experienced as wind is therefore the visible expression of energy redistribution across the planet. Air movement transports heat from equatorial regions toward the poles, moderating temperature extremes and maintaining climatic stability. The atmosphere's global circulation is organized into large-scale cells that operate predictably across latitudes. The Hadley cells dominate tropical regions, driving trade winds that historically facilitated maritime exploration and global trade. The Ferrel cells influence temperate climates, while polar cells regulate cold air movement near the poles. High-altitude jet streams, narrow bands of fast-moving air, act as steering mechanisms for weather systems. Their position and strength influence storm trajectories, precipitation patterns, and even aviation efficiency. Human societies have long been shaped by these atmospheric patterns. Agricultural productivity, settlement distribution, and trade routes have all depended on prevailing winds and climatic consistency. Thus, atmospheric circulation is not merely a physical system, but a historical force shaping civilization. Before the emergence of modern science, air was conceptualized as a metaphysical substance rather than a material one. Ancient Greek philosophy described it as Pneuma, a vital breath animating both body and soul. Similar concepts appeared independently in other cultures, such as Qi in Chinese philosophy and prana in Indian traditions. These interpretations framed breath as a conduit of life energy, linking physical existence to cosmic order. Breathing practices were developed not only for health, but for spiritual alignment, reflecting an intuitive recognition of air's importance. Although lacking empirical measurement, these early frameworks acknowledged air as a powerful, invisible force essential to life and consciousness. The scientific understanding of air underwent a profound shift during the 17th and 18th centuries. Experiments by Torricelli demonstrated that air exerts pressure, challenging the notion of atmospheric emptiness. Boyle's investigations into gas behavior revealed predictable relationships between pressure and volume. Later, Priestley and Lavoisier identified oxygen and clarified the composition of air as a mixture of gases rather than a single element. These discoveries laid the foundation for modern chemistry and atmospheric science. Air became quantifiable, measurable, and subject to empirical analysis, transforming it from a metaphysical concept into a scientific object. As measurement tools improved, the study of weather evolved from observation to prediction. Cloud classification, temperature measurement, and pressure monitoring enabled systematic analysis of atmospheric behavior. In the 20th century, advances in radar, satellite imagery, and computational modeling revolutionized meteorology. Today, complex algorithms simulate atmospheric processes, allowing forecasts with increasing accuracy. This predictive capacity underscores humanity's growing understanding of atmospheric dynamics, though uncertainty remains inherent due to the system's complexity. Industrialization introduced unprecedented changes to atmospheric composition. The combustion of fossil fuels, deforestation, and intensive agriculture released large quantities of greenhouse gases and pollutants, disrupting natural cycles. Carbon dioxide concentrations have risen significantly, altering Earth's energy balance. Particulate matter and chemical pollutants degrade air quality, affecting human health and ecosystems. Today, the majority of the global population breathes air that does not meet established safety standards, highlighting the atmosphere's vulnerability to human activity. The accumulation of greenhouse gases has triggered widespread climatic shifts. Rising temperatures accelerate ice melt, raise sea levels, and intensify extreme weather events. Changes in atmospheric circulation disrupt rainfall patterns, affecting agriculture and water resources. These impacts cascade across ecological and socio-economic systems, increasing the frequency of displacement, resource scarcity, and environmental conflict. Climate change is therefore not a singular issue, but a systemic transformation of Earth's life support systems. In response, societies are developing strategies to mitigate atmospheric damage. Renewable energy technologies reduce reliance on fossil fuels, while carbon capture systems aim to remove excess carbon dioxide from the air. Urban planning increasingly incorporates green infrastructure, and conservation efforts seek to restore natural carbon sinks. These initiatives represent attempts to realign human activity with atmospheric limits. The atmosphere is a shared inheritance, circulating across generations without regard for borders. The air breathed today has sustained life for millions of years, and will continue to do so if preserved. Protecting atmospheric integrity is therefore an ethical responsibility extending beyond immediate concerns. Decisions made today will shape the conditions under which future generations breathe, live, and thrive. Air is not merely a background element of existence. It is the connective tissue of the biosphere, linking individual respiration to planetary systems. Every breath participates in a cycle that spans cells, ecosystems, and centuries. To understand air is to recognize humanity's position within a vast, interconnected system. Protecting the atmosphere is not simply an environmental task. It is the preservation of the conditions that make life possible. Every breath carries history, and safeguarding that history is a collective responsibility.